We're going to continue with our look at the second law where the sum of the forces equals 0 or the sum of the forces equals ma. Those are our only two choices for this situation. Now what we see here is Mr. Seba is lifting up on a box. It was a 10 kilogram box. It's the same box we've been talking about since the last video. But he doesn't lift it up. You can imagine, just putting a little bit of force on something, but not quite lifting it up. So the first order business is to draw that free body diagram. Free body diagram, we'll abbreviate it FBD. So he pulls upward with a force of, I'll put it over here, 40 newtons. Gravity pulls down. He didn't lift it off the table, however. Since he didn't lift it off the table, there's still a normal force. They call it Fn, or I like little n more often. So since the box isn't moving yet, there's no acceleration, it's a constant velocity of 0. The sum of the forces is 0. So we bring that 0 down, and we say normal is going upward in the positive y direction. So is the normal force. But mg is opposing, and it's going downward. So that's how I got my positives and negatives, and I know mg is 98. And I know that from the previous video because we said, 10 times 9.8. Now it's just some simple algebra. And it's 58 newtons. Normally, if he weren't pulling on the box, it would be 98 newtons. But you can imagine because he's lifting up a little bit, it's basically he's taking a little bit of stress off the table. The table doesn't have to support the box quite as much as it normally would. So that's a big help. Now he's going to pull upward with a force of 100 newtons. The box only weighs 98. So if we draw a free body diagram, 100 newtons goes up, 98 newtons goes down. This is mg, and this is the force of his pull. Because the force of his pull is greater, he can lift the box up. So in this case, the sum of the forces in the y direction is ma. So it's 100 newtons up minus mg going down. And let's see, I just started to substitute. So we knew the mass of the box. We knew the 100 newtons from his pull going up, minus 98. And I think obviously we can see this is going to be 2 over here. 100 minus 98 is 2 newtons. Divided by 10 is 0.20 meters per second squared. He's going to be accelerating the box. He's going to be giving the box an acceleration as he lifts it off the table. Now here's another situation. A 2 kilogram ball is thrown into the air with a force of 30 newtons. So let's draw a free body diagram. So let's just draw a little cartoon picture. We have a ball. I don't know if it's like a basketball. And we're throwing it into the air. There's our hand, just real quickly, throwing it up into the air. So while we're throwing it, gravity pulls down, and the force of our hand goes upward. Once the ball leaves our hand, it's no longer in contact with our hand. So once it's above our hand, once we've thrown the ball, the only force acting on it is gravity. You might say, well, didn't you give a force to the ball? No. There's no way I can magically have a force go from my palm into the ball. The force is only exerted on the ball while I'm holding it, while you or I are touching the ball. It's a contact force. Once we release the ball, it's gone. Okay, so let's get the acceleration. This is while being thrown. So while we're throwing the ball, the sum of the forces in the y direction is ma. And let's see what we know. We're going to bring down that MA. We have to make our equation. Force of the hand goes up. It's in the positive y direction. But mg goes down. So let's see. I know the mass of the ball is 2, but I don't know the acceleration. They told us the force of our hands was 30 newtons. And let's see, do we know the mass of the ball? Yeah, it's 2 kilograms times 9.8. So at this point, it's just some algebra. 2 times A is, let's see what we get. 30 minus 2 times 9.8, which is 19.6. You've probably seen that so many times, is 10.4. Divide over the 2. Oops, I'm a little close to the edge of the PowerPoint there. And I get an acceleration of 5.2 meters per second squared. Well, let's try one more of these, and that'll probably wrap up the video for today. It says calculate the mass of the 735 Newton box of tea. That's a pretty heavy box of tea. That would probably be like a case of them or something. Well, in this case, the only force we're talking about is the weight. So we go back to our weight equals mg. And the variable we don't know is the mass. So it's weight over gravity. We know the weight. It's 735 newtons. And remember, a newton is a kilogram meter per second squared. Gravity, 9.8 meter per second squared. Now let's estimate. 9.8 is really close to 10. So 735 divided by 10 would be 73.5. Well, we're not dividing by exactly 10. So that's 75 kilograms. Totally seems very reasonable. Now, maybe I'm tired from lugging that big box of tea for myself, and I sit down on it. It says calculate the normal force from the earth on the bottom of the box. To do this, we're going to need a free body diagram. We can't do this one on our own without a free body. So mg goes down. The normal force of the earth goes up. But I'm sitting on the box. And it says I'm exerting a 560 Newton force sitting on the box. Now the box isn't going to move. We're going to assume that it takes my weight, no problem. So it's at a constant velocity of 0. So 0 equals, let's see, let's do the positive one first. Normal goes up, so that's positive. mg goes down. And so does my weight of the 560 newtons. At this point, it's just substituting. Let's see, we want to know the normal force. The mg, we could either let's calculate it from the 75 kilograms times 9.8, although we know what it is, minus 560. So 0 is normal minus, and we have to see what that number works out to, and it works out to 1295 newtons. So add that to the other side, and the normal force is 1295 newtons. It's significantly higher than the mass of the box because I'm sitting on it. Because I'm sitting on it and exerting a force down, the Earth has to push back even more with a higher normal force.